Alright, now welcome to our journey into the heart of star formation. Now we are exploring the Orion Nebula, also known as M42, one of the most famous star forming regions in our galaxy. So as we go through this slide, imagine looking up at Orion's sword on a clear winter night, seeing a faint glowing patch of light. That fuzzy glow is actually a bustling nursery of stars. Now first, here on the slide, you can see a visible light image of the Orion Nebula. Notice the bright central area. That's where the trapezium cluster lies, a small group of extremely young and massive stars. And surrounding them, you can see glowing filaments of gas and dust, almost like the nebula is breathing or churning. And the nebula stretches across roughly 26 light years. So it's huge. So keep in mind, this is just the part we can see in visible light. There's much larger cloud hidden behind it, full of stars still forming. Now the Orion Nebula is in the Orion sword. Even with binoculars, it glows, and through a telescope, it's breathtaking. And this glow comes from massive stars ionizing surrounding gas, lighting up the nebula. Now notice that hundreds of young stars are forming here, and the trapezium stars, less than 2 million years old, dominate the nebula's light. So they are so young compared to our sun's 4.6 billion years. And the Orion Nebula spans about 26 light years. Huge. If our solar system were inside, it would be a tiny in comparison. Now we know that many stars are forming deep inside dense clouds called molecular clouds. And these protostars are cool and faint at visible light, so we can't see them here. But astronomers use infrared and radio waves to see through the dust, revealing hundreds of hidden protostars and mapping the structure of these massive clouds. Now when talking about star formation periods, stars form quickly in astronomical terms, only a few millions of years. And that's short compared to their billions of years main sequence life. So this makes regions like Orion perfect for studying star formation as it happens. So this glowing Orion Nebula is just the tip of an iceberg, and behind it, dense clouds hide many protostars. Now think about this. If most stars are hidden in gas, how do astronomers find them? Infrared and radio observations are key. We will see examples next. Now that we have seen the Orion Nebula from the visible light perspective, let's explore what's really happening inside this stellar nursery. Remember, the glowing cloud we saw before, it is just the surface. Most of star formation is hidden behind thick dust and gas. Now this slide shows both a conceptual illustration and infrared observations that reveal the unseen in action. So let's dig in. First, this diagram shows the trapezium stars at the center, the expanding ionized hydrogen around them, and the surrounding molecular cloud. So within the cloud, you can see protostars forming. These are stars in their earliest stages. Now the bottom left inset shows a near infrared image, revealing more than 50 low mass protostars that are invisible in visible light. So together, these images helps us understand how the visible nebula is just the tip of much of a larger active star forming region. So part of the nebula we see in visible light is just a small ionized pocket on the near side of a vast molecular cloud. And the trapezium stars at the center produce intense radiation that pushes the gas outward. So as the gas expands, it compresses nearby regions of the cloud. And this compression can trigger new protostars to form, giving the cloud a kind of ripple effect. one generation of stars can help create the next. So even the visible glow is just part of a dynamic, ongoing process. Now what makes this glow possible? That brings us to the stars themselves, and especially the most powerful one in the trapezium cluster. So among the trapezium stars, the hottest is NO6 stars, about 30 times the mass of the Sun with a surface temperature of 40,000 Kelvin. And this star emits ultraviolet light with wavelengths shorter than 91.2 nanometers. Just enough energy to ionize hydrogen and make the nebula shine. But without this one star, the visible nebula would disappear almost instantly. So the overall appearance of the nebula is directly tied to the energy output of these massive stars. But visible light only tells part of the story. To see the true scale of star formation in Orion, astronomers rely on what observations? Infrared observations. Now we already know that infrared imaging penetrates the dust, revealing hundreds of hidden protostars and warm dust. For example, the BN object is a young B-type star just reached in the main sequence. And the KL Nebula contains a cluster of cool young protostars. And in fact, about 85% of the young stars in the region are surrounded by disks of gas and dust. Now the radiation from the trapezium stars gradually evaporates these disks, shaping elongated structures called protoplanetary disks. So these images show that the star formation is active and ongoing, hidden just out of sight in visible light. So what we see with our eyes is only a part of Orion's story. But infrared observations reveal a bustling nursery of hundreds of protostars forming in the molecular cloud. Now you can pause and imagine. Hundreds of protostars hidden in the cloud, while the intense radiation from the trapezium stars sculpts their surroundings. And this is star formation happening in real time, both beautiful and powerful. Alright, now so far we have seen how stars form in molecular clouds and how massive stars in the trapezium power the visible glow of the Orion Nebula. But star formation is not just a local event. It can actually trigger more star formation nearby. And this process is often called contagious star formation because one generation of stars can ignite the next, spreading like a cosmic chain reaction. First, let's discuss these images. Here, this figure shows star formation pillars in the 30 Doradus star cluster. Part A combines ultraviolet, visible and infrared light to show three pillars of gas pointing back toward the massive hot stars. And part B is just an illustration of how these pillars form. Intense UV radiation and fast-moving stellar winds hit the surrounding gas, but denser blobs protect the material behind them, creating these elongated structures. So the pillars can stretch for several light years and contain dense regions that may collapse into new stars over the next few million years. So massive stars produce huge amount of ultraviolet radiation and powerful stellar winds. And when these push into nearby gas clouds, they compress the gas. And next, this compression creates the star formation pillars we see in this image. And notice the pillars point back toward the hot stars that are sculpting them. And within these pillars, slightly denser blobs can collapse under gravity, forming new protostars. So essentially, the birth of one generation of stars sets the stage for the next. But radiation and stellar winds are not the only triggers. The life and death of massive stars can continue this chain reaction in an even more dramatic way. Remember, when a massive star explodes as supernova, it sends shock waves rippling through nearby interstellar clouds. And these shock waves compress the gas, causing part of the cloud to collapse and form new protostars. So this means starbirth can propagate across entire regions of nebula, creating multiple generations of stars. Now in some massive clusters, this process can continue over millions of years, spreading star formation like a chain of cosmic dominoes. So in regions like 30 Doradus or even the Orion Nebula, star formation is not isolated. It spreads. And massive stars can both illuminate and sculpt their surroundings and even end their lives, triggering the next generation of stars. Now take a moment to imagine. These pillars are full of dense blobs, each a potential new star. And all of this was set in motion by stars that already formed, creating a cascading chain of stellar birth. It's like a cosmic ripple effect across the nebula. Now in the last slide, we saw how massive stars can trigger new stars through radiation, winds and supernova. Now let's step back and look at the bigger picture. How star formation can propagate through entire regions, creating successive generations of stars over millions of years. So here the figure A, it shows the N11B star forming region with a visual and near infrared image. Now here you can see dense pockets of gas where new stars are forming, compressed by the radiation and winds from older massive stars to the left. And in the upper right, small block globule appears, potentially forming future stars. And in the image B, it shows Westerland 1, a super star cluster containing around 500,000 stars, including some extremely massive ones. Now imagine being inside it. The night sky would be filled with hundreds of stars brighter than the full moon. So these images illustrate how compression from one generation of stars can ignite the next, repeatedly shaping entire regions. Now, all the massive stars compress nearby gas clouds as they emit UV radiation and stellar winds. And in region like N11B, this compression triggers new stars to form in dense pockets. So these newly formed stars can in turn compress adjacent clouds, starting the next generation of stars. Now this ripple effect can repeat over millions of years, gradually building multiple generations of stars across the nebula. And sometimes these successive generations result in clusters so massive they are truly extraordinary. Now here, Westerland 1 is a prime example. It contains approximately 500,000 stars, some of which are extremely massive, and it formed in less than 5 million years. An astonishingly rapid burst of star formation. So this shows how intense and concentrated the process can be when multiple generations of stars trigger one another. It's like a chain reaction on a grand scale, producing entire stellar cities in the galaxy. So from N11B to Westerland 1, we see the full power of successive star formation. All the stars shaping the environment, compressing the gas and creating new stars, sometimes building entire clusters in just a few millions of years. Now before moving into the next slide, think about this. In some regions, star formation spreads like ripples around a pond. So each generation builds on the last, creating a cosmic timeline written in the stars. Now where do you think the next generation of stars might appear in Orion? They will most likely appear in the denser regions of the molecular cloud surrounding the existing nebula, especially behind or around the areas where the trapezium star's radiation and winds are compressing the gas, just because these regions are still full of dust and gas. Alright, now we have explored how star formation starts, spreads, and triggers new generations. Now let's look at the bigger picture. Orion itself as a dynamic, evolving stellar nursery. So star formation here is not a single event. It's an ongoing story that has been unfolding for millions of years and will continue into the future. Now here's a composite image of Orion's star forming regions. On the top right, you can see a near infrared panel showing fingers of gas, sometimes called the hand of God, where protostars are embedded in the cloud and gas is being pushed away by radiation. And the bottom right inside shows the BN object, a B-type star just reaching the main sequence, and the KL Nebula, full of cool, young protostars. So these images show stars at different stages of formation, highlighting the ongoing cycle of star birth. Now Orion's star didn't all form at once. The oldest stars near Orion's west shoulder are about 12 million years old, and the stars in Orion's belt are younger, around 8 million years old. Now at the center of the Great Nebula, the trapezium stars are the youngest, only about 2 million years old. So this tells us that star formation has been sweeping across Orion over millions of years, moving from northwest to southeast. So it is a cosmic wave of creation in action. But this wave is not finished yet. The Orion Nebula itself will keep evolving, and embedded protostars will eventually ionize surrounding gas and create new visible nebula, just as the trapezium stars did. And at the same time, massive stars will push and disperse the remaining molecular cloud. Now this ongoing cycle, compression, star formation, and feedback from massive stars will continue until the gas supply is exhausted. So, Orion is a living, breathing stellar nursery, constantly renewing itself and producing new stars for millions of years. So, from the oldest stars near Orion's shoulder to the newborn trapezium stars and the hidden protostars still forming today. So, Orion tells us the story of star formation as a continuous, dynamic process. And by studying it, astronomers can watch stellar nurseries in action and understand how stars like our Sun are born. Again, take a moment to imagine. New stars will emerge, nebula will appear and fade, and gas clouds will be sculpted by powerful radiation, all in a cycle that has been running for millions of years and will continue into the future. So Orion is a cosmic story still being written in real time. Okay, now with this, we conclude the section 2 of our chapter. Now to sum up, the Orion Nebula and its surrounding molecular cloud offer a vivid picture of star formation in action. Stars form deep inside dense clouds, hidden from visible light, but infrared and radio observations reveal hundreds of protostars and dusty disks. And massive stars like those in trapezium both illuminated the nebula and trigger new star formation, creating successive generations across the region. So star formation has swept across Orion over millions of years, and the process continues today, shaping the nebula and producing stars at different stages of evolution. So in short, Orion is a living stellar nursery, dynamic, ongoing, and a perfect laboratory for understanding how stars are born.